So let's consider the case, for example, with total internal reflection using a prism. But wait a minute, what do I mean using a prism? Well, if you have binoculars, then what happens is for one type of binoculars that use prisms, you've got the big front end, but then the apertures here are too far apart for your eyes. Your eyes are closer together. And so what happens is you've got to get the images up close here to where your eye can see them. And so the way that that works is that you have a prism here, and then you have another prism right there. So the light comes in, reflects. Actually, I guess this other prism is going to look like that. Looks like that. So the light comes in, reflects, goes into your eye. And so likewise over here, we have a prism here, and then we have a prism right here, and the light comes in, reflect into your eye. Okay, and so now why not use a mirror to reflect the light? Well, it turns out that with total internal reflection, you have 100% reflection. The mirror actually has a little coating on it, and you don't really get 100% reflection typically from a mirror. And so you always lose a little bit, and so the prisms are considered a better way of doing it. It also works for it's better color resolution, many different reasons the prism is considered superior. So if we have a prism, and let's make it a simple prism, so this is going to be a 45-degree prism right here. So 45 degrees and then a right angle right there. So we want the light to come in here and reflect off that surface. Now, assuming the light is coming in perpendicular to this front surface, I want to know what is the minimum index refraction that gives you total internal reflection right there. Okay, so it turns out to be pretty simple. We know that the critical angle for total internal reflection is the inverse sine of N2 over N1. And so we can just do a little algebra there and say, okay, so N1 sine theta C equals N2. Okay, and so we're trying to actually solve for N1, okay, because N2 is the N that's outside. So that means that N1 is going to be N2 over sine theta C. Now, if we assume it's air outside, the index refraction is approximately 1. Now, if you go out enough decimal places, it's not 1, but we're not going to go out that far. All right, so N1 is going to be the N that we're interested in is going to be 1 over sine of theta C. Well, theta C is this angle right there. Well, you can look at this and realize that that angle has to be 45 degrees if you do the geometry right there. Okay, if that's a right angle, then that's going to be 45 degrees. That's a right angle, so that's going to be 45 degrees. Okay, so that means that the N turns out to be equal to 1.41. Okay, so if you have an index refraction that's bigger than that, then your glass will actually be used as a prism for this. Now, the thing is that if you had light coming in at a slightly greater angle like this, in other words, you're looking at something that's a large object, then what would happen is that this angle would exceed the critical angle. You get total internal reflection, but something coming from this direction would actually refract through. So really, in order to look at things that are not just straight ahead, you probably want an index refraction slightly larger than that in order to compensate for looking other than directly ahead. Now, part of this is also that you have the aperture up here, the lens, and so you got to take that into account as well. So normally your prisms are going to have a little bit greater than 1.41. The bigger the index of refraction, typically the more expensive the glass, in the prism, but the clearer the view is going to be, and the more it's going to be able to accept the possibility of off-axis things. This is one way you test a good pair of binoculars. You hold it out at arm's length and make sure that the light cast by the aperture is a circle. But what if your prism is underwater? Because what would happen is we derive that for n equals 1 outside. What if we're underwater? So what if this is water out here? Okay, well, n of water is 1.33. So same thing, same sort of situation. We want total internal reflection. We want that to be a 45-degree angle, so 45-degree prism. And so now it actually turns out to be very simple. Okay, so the n1 equals n2 over sine 45 degrees. It's just now n2 is 1.33 sine 45 degrees. And so that means the index of refraction is going to be 1.88. So if you wanted to use binoculars underwater for some bizarre reason, then you would need much greater index of refraction. Okay. Now, suppose that you have some pretty nice glass here. And so let's say that it's got an index of refraction of 1.65, but it is underwater. So the n outside, so n2, is going to be equal to 1.33. So this is underwater out here. So now the question is, for light coming in, what does it do? Well, clearly, this is less than the critical 1.88 we just derived. So what that means is, again, this is 45 degrees right here. That means that this is going to refract instead of reflecting. Okay. And so what you would want to do now is figure out the angle of deflection. So the angle of deflection is this right here. Well, if we use Snell's law, n1 sine theta 1 equals n2 sine theta 2. Okay, so this will be my n1, n2 will be outside. Okay, so this angle theta 1 is going to be 45 degrees. And so that means that we can say that n1 sine theta 1, n1 sine theta 1 divided by n2, and then take the inverse sine of all that, that's going to be theta 2. So that would be the inverse sine of 1.65 sine 45 degrees divided by 1.33, and that gives you 61.3 degrees. Okay, so what I've got here is, I now know this thing comes in right there, okay, and it deflects, so this angle is 61.3 degrees. Well, if I draw a line straight through, then that angle right there has to be this angle, which is 45 degrees. So that's the angle of deflection. So angle of deflection will be 61.3 degrees minus 45 degrees. So the angle of deflection is going to be equal to 16.3 degrees. Okay, so here we have application of prisms again. Okay, and so we're not using it to disperse light. Now really what would happen is we would actually have some dispersion right there and different colors being refracted differently, but we're not going to worry about that for this problem right here.